Hello everybody, welcome back to MrMiers Math Channel. Today what we're going to talk about in Chapter 7 is Section 7.2, which is Properties of Rational Exponents. Alright, so let's get started. So first we have the product and quotient property to simplify radicals. The product property states that the nth root of a times b just equals the nth root of a times the nth root of b. And the quotient property states that the nth root of a on b equals the nth root of a on the nth root of b. We use these properties to simplify our radicals. Sometimes it's easier to combine radicals or split them up depending on what we know. And in order to use these properties, the index has to be the same for the radicals. So for us to combine two radicals like in the product property, n has to be the same, or the index has to be the same. All right, so let's get to some examples. Some are going to be easy, and then we're going to heighten the difficulty with each one. All right, so in example 1, in part A, we have the cubed root of 3 times the cubed root of 9. All right, so we can use the product property to rewrite this as the cubed root of 27. And then from there, like I've said in previous sections that we've covered, this is one that we'll really commonly see, the cubed root of 27. And we should know what that is, but remember, it's whatever number we can multiply 3 times and get 27. And that, through some trial and error, we could get 3. All right, then the cubed root of 2 times the cubed root of 4, that would be the cubed root of 8. Remember, we're just using that product property. And then the cubed root of 8 is 2. We're going to combine these as well. So the fifth root of 4 times the fifth root of 8 is the fifth root of 32. And the fifth root of 32 is just 2. Now in part D, we have the cubed root of 20 times the cubed root of 14. 20 times 14 is 280. And now from here, we're going to have to simplify. In order to simplify, we have to remember how we can simplify some radicals. So we could use a factor tree. All right, we could take out the biggest perfect squares, or we could take out the lowest primes. I'm going to go with the lowest primes, especially for radicals that don't have an index of 2. All right, so 280 is just 2 times 140. 140 is just 2 times 70. 70, 2 times 35. And I like to cross them out as we go. So this is what we have left over. And remember, we're taking the cubed root, so we're looking for 3 of the same number. We've got that in our 2's, so 2 comes out, and then 35 is left inside the radical. So that's 2 times the cubed root of 35. Awesome sauce. So that was the product rule. Now for our quotient rule, we're just doing the same thing. We're either combining or separating it using the quotient rule. So in part A, we're going to combine this. So 48 divided by 3, that's going to give us 16. So we have the fourth root of 16, and the fourth root of 16 is 2. And then in part B, we have the fourth root of 3,125 divided by the fourth root of 5. So 3,125 divided by 5, 625. So we have the fourth root of 625, which is just 5. In part C, 54 divided by 2 is the cubed root of 27 there, which once again is just 3. So far, we've already looked at this one at least 4 times by the time we started this chapter. All right, and then in part D, notice it's already combined, so maybe it's helpful if we separate it, especially because we haven't had any experience so far, not in my lectures, with any root of a fraction. All right, so let's separate it using division. We have the fourth root of 1 on the fourth root of 16, and conveniently enough, okay, we can simplify this. The fourth root of 1 is 1. The fourth root of 16 is 2, so that's just 1/2. Awesome sauce. So these are just some basic problems using these properties. And of course, we're going to ramp up that difficulty. Reminder, in order to use those properties that we just looked at, they've got to be the same type of radical. So both square roots, both cube roots, fourth roots, fifth roots, and so on. All right, now we're going to get into simplifying some rational exponents. So I'm not going to talk about each one of these explicitly here, but these are some properties that we've talked about in Chapter 6, which is our chapter on exponents. So we've already reviewed some of these properties. So here's the list of the properties, and we're going to go out and use them. All right, so we've got like power rule, power of a power rule, product rule, quotient rule, negative exponent rule, zero exponent rule, all that good stuff. All right, so in part A of example 3, remember, in order to use these rules, the base has to be the same. So we have 6 to the 2/3 times 6 to the 1/3. We're going to add those exponents using the product rule. That's 6 to the first power, which is just 6. In part B, we have power rule, so we're going to multiply these exponents. If we multiply those exponents, we just get 3. So 3 to the third power is 27. In part C, we're going to apply that power to each factor, right? So 16 and 25. So it's going to be 16 to the 1/2 power times 25 to the 1/2 power. A lot of people say distribution, but I like applying the power to each factor. All right, I think that's a little bit more explicit. Now from here, 16 to the 1/2 power is just the square root of 16, which is 4. Same thing here. So the square root of 25 is 5. So this is really just 4 times 5, or 20. All right, in part D, notice we have a negative exponent. Let's get rid of that. I like getting rid of those negative exponents first. So in order to get rid of that negative exponent, what we're going to do is put that quantity on the other side of the fraction bar. So whatever's in the numerator is going to go to the denominator. Whatever's in the denominator is going to go to the numerator, because this whole thing is raised to a negative exponent. So it's really just 8 on 27, that whole thing raised to the 1/3. Now we've got to apply that exponent to both the numerator and denominator. So 8 to the 1/3 is just the cubed root of 8, which is 2. 27 to the 1/3 is the cubed root of 27, which is 3. All right, now in part E, this is just using quotient rule here. All right, they have the same base, so we can simplify this. 5/2 minus 1/2. We're going to subtract those exponents. That would be 4/2, or 2, and 7 squared is 49. Awesome. Now we're going to get into more complex expressions where we have both variables and integer coefficients. Oops. So in example 4, part A, we can really just break this down into two independent radicals. All right, this is essentially using our product property, and now we can simplify them each. So the square root of 9, we know that's 3. Now the square root of x to the 6th may be kind of tricky. All right, so remember the index is 2. So what we're really looking for is how many pairs of x's could we take out. Now x to the 6th is literally x multiplying 6 times. So when we're thinking about how many pairs come out, that's 3 pairs. So x times x times x, or x cubed. If we take a look at B, once again, we can separate this out, the cubed root of x cubed, and then the cubed root of y to the 6th. Now once again, how many sets of 3 are going to come out in the numerator? That's just 1, so it's just x to the first power. And then how many sets of 3 are going to come out in the denominator? That's 2, so that's y squared. In part C, same thing. We have the square root of x to the 6th on the square root of y squared. All right, remember the index is 2, so we're looking for pairs. There's 3 pairs that are going to come out in the numerator, just 1 in the denominator. So we have x cubed on y. And lastly, in part D, if you want to simplify this all at once, you don't have to split it up. That's just an extra step. The square root of 25 is 5. The square root of y to the 4th would be y squared. Now something else that's often helpful, because for each one of these, we had an exact amount of pairs that came out. That's not always going to happen. One thing that we could do, let's say if we had the square root of y to the 7th here, is we could just figure out, okay, how many sets of 2 are there? And one way to do that is just, let's divide 7 by 2. Okay, classic long division. If we do that, we've got 3 sets, 1 remaining. That means y cubed would come out, and then we would have just the square root of y left over. So we would have 1y left over inside the radical, 3 sets coming out. All right. All right, now we're going to use some of those rational exponents. Okay, so we're going to apply that power to each one of these factors. Oops, wrong button there. So we have 4 to the 1/2 times y to the 6th to the 1/2. Remember, you can cut down some of these steps by doing a little bit more at once. So y to the 6th to the 1/2 is just going to be y cubed, because we're going to multiply those exponents. And then 4 to the 1/2 is the square root of 4, which is 2. Now we've got to use some quotient rule here. So we got to simplify the a's, since they have the same base, and the c's. Remember, that c and that a always have an implied power. So the implied power there is 1. All right, so we have a to the 3/2 on a to the 1st. We're going to subtract those exponents. We're going to get 1/2 left over. All right, and then we have c to the 1st on c to the -2nd. 1 minus -2 would be 3. So 3a to the 1/2 c to the 3rd. All right. Moving on here. Now, in order to add these expressions or subtract these expressions, once again, they've got to be like terms. Okay, so in order for them to be like terms, this part has to be the same. I always talk about these things as like items. Okay, we're going to add the same type of items together. It's just that analogy of adding apples and oranges. Okay, we can't add apples and oranges. You know, 2 apples plus 5 oranges doesn't make 7 oranges or 7 apples. Okay, so it's got to be of the same type. All right, so in both of these, we have cubed roots of x. All right, we have 3 of them right here. We've got 1 of them right here. So when we're adding them, we're going to have 4 in total. 4 times the cubed root of x. Same thing right here. The index has to be the same. We've got to be talking about the same things. It's just like taking inventory. We have 8 of these items. We're going to get rid of 4. So we have 4 of these items left over. Same goes here. 6a to the 2/3 power minus 4a to the 2/3 power. That's 2a to the 2/3 power. Awesome sauce. Last example's up. So in this last one, we have the square root of 12 plus the square root of 12. Obviously, there's 1 square root of 12 plus another, so that would be 2 square roots of 12. But now we're not done yet. We still got to simplify. All right, the square root of 12, that's something that we could simplify. If we make our factor tree, we've got 4 and 3. Okay, and then the square root of 4 is 2. So this is 2 times 2 root 3. And I could have kept going on that factor tree. So that's how we got the 2 root 3. And then 2 times 2 is 4, so that's just 4 root 3. Same here in part B. We're going to have negative 1 root 12 minus 2 root 12, so that's negative 3 root 12. We just got done simplifying root 12, so we can replace root 12 with 2 root 3. So this would leave us with negative 6 root 3. All right, folks, if you found that helpful, if you enjoyed it, please like, subscribe, share. Thank you, and have a great day.